In test problems, we can show very easily that Arepo has a lot of demonstrated advantages in terms of how it's able to handle a lot of hydrodynamic phenomena. But the real question we have for today, and where I've contributed some work, is to look at how Arepo performs on galaxy formation problems. So this has been work that's been done with a lot of folks who are here at the CFA, some who have moved on since, within the context of the Gadget Arepo comparison project. So the specific task that we set out for here was to compare the performance of two simulation codes that are nearly identical in all of their characteristics except for the hydrosolver that they apply. So Gadget and Arepo are both written by Volker Springel. They have nearly identical backends, so they use the same gravity solver, they start from the same initial conditions, and they include the same physics, things like radiative cooling of gas, star formation prescriptions, etc. The only real difference between these two codes is the hydrosolver they apply, and it's a radically different hydrosolver. So we can basically run two side-by-side simulations and see how the hydrosolver is impacting the resulting galaxy populations that form. Now, if we do that, this is the result. This is a plot taken from a paper by Mark Vogelsberger. On large scales, this is showing the gas distribution in Arepo on the left and in Gadget on the right. And these two plots look nearly identical. The reason for that is that on large scales, the gas distribution is very similar between these two codes because it's driven by the gravitational collapse of structure. Hydrodynamic phenomena are subdominant on these large scales. As you push down towards the halo scale, what you find is that, again, you're looking at Gadget on the left. We've got a temperature plot and a density plot of the gas. We find that the halo gas around galaxies in Gadget is hotter and is more abundant than the halo gas around the same galaxies in Arepo. And if we push down to even smaller scales, we look around the galaxies themselves, what we find is that the spatial distribution of gas within Arepo tends to be smoother and more spatially extended than the counterparts in Gadget. And this is the scale where I focused my attention. So if you look at a number of galaxies, that was for one specific example, you find this is a ubiquitous result. That galaxies, the gas disks in galaxies can be substantially larger in Arepo compared to their matched companion in Gadget. So you have all this gas in the halo in Gadget, which is basically here just showing up in a gas disk. This is showing for 5 examples, but in fact you can generalize this and show that in the simulation volume this is true for hundreds, if not thousands, of galaxies. So what's actually driving these differences? Well, at the time when we first were doing this comparison project, it was somewhat unclear what the major differences between these two codes were. However, in hindsight, there's a lot of very obvious tests you can do which show that you shouldn't expect at all to get the same answer between these two codes. One example is looking at a Kelvin-Helmholtz instability. So this is showing a Kelvin-Helmholtz instability. I'm going to have dense fluid moving to the right here and diffuse fluid moving to the left here. These 3 panels just show Kelvin-Helmholtz instabilities with different thicknesses for the inner band. That's the only difference. On the top, I've got Arepo, and on the bottom, I have Gadget. So one might imagine this could represent cold gas coming in from the intergalactic medium flowing into the CGM hot halo. Well, what happens in these two simulations? In Arepo, we find that we have billows developing, which quickly shred the cold material and efficiently mix the two phases. In Gadget, we find that an artificial surface tension term tends to stop mixing between these two phases, and we end up getting to building up these blob-like structures, which don't mix almost at all with the diffuse hot gas. So what's the result in cosmological simulations? Well, this now shows a cutout from one of the systems within the comparison project. We're showing large-scale gas distributions here on the left. We have nested views going down to small-scale gas distributions on the right. From the first snapshot, you can see we have relatively large gas disks in Arepo, but what I want you to focus on is all the blobs that exist down here. These blobs, you can watch their subsequent evolution, where they're actually going within this simulation. In fact, these blobs are very efficiently migrating to the bottom of this potential well. What's happening is that these start as mild overdensities in the IGM that fall into the circumgalactic medium, or the hot halo, and are pressure confined. That causes them to radiate away their energy. And while they should be disrupted due to Kelvin-Helmholtz and Rayleigh-Taylor instabilities, those instabilities are suppressed in Gadget. As a result, they lose their orbital energy and angular momentum to hydrodynamic drag, and they end up providing a source of cold, low angular momentum fuel to these central galaxies. So whereas my primary mode of accretion over here is cooling from the hot halo, here I have an additional channel of accretion, which is from these cold blobs as they migrate to the center of this potential well. And that can be quite profound in terms of the ending properties of these galaxies. Now, to make the comparison a bit more statistical, we actually fit exponential profiles to the gas disks in these two simulations. So this is showing the central surface density versus the disk scale length from these simulations. The gas disk best fit parameters for Arepo are shown in red, and the best fit parameters for Gadget are shown in blue. You can see a histogram up here which shows the projected distribution of those disk scale lengths. There's a clear offset, where the disk scale lengths for the Arepo galaxies are substantially larger than those that you find in Gadget. And so that's a reflection of the images that I've shown you previously. So we can really break this down at the end of the day and ask what drives these differences. Well, I talked for one about fluid instabilities. That plays a really central role. The inability of Gadget to disrupt the cold gas as it comes into these hot halos is fairly disruptive to the gas disks that form. And if you want to have more spatially extended gas disks form in Gadget, you have to improve the way that fluid instabilities are handled there. There's a second effect, which I didn't yet talk about, but I'll mention here. It's the viscous heating of halo gas. So what happens here is that turbulent power is injected around the virial shock. When you inject that energy, it should cascade down to smaller scales. But rather than it cascading down in Gadget, what you actually find is there's a truncation of the turbulent power cascade, where you actually end up depositing or thermalizing a lot of that turbulent energy close to the virial shock. That's one of the reasons why you have more gas and hotter gas in the Gadget galaxies compared to the Arepo ones. And then there's the issue with fluid phase boundaries. This one's also fairly severe. What happens is that as you have cold gas disks rotating within hot halos, there's a viscous interaction between those cold gas disks where you basically transport some of your angular momentum to the hot halo. And that torques down the cold gas disk at the expense of the hot halo. So we can ask the question, are all Gadget SPH results wrong? Giving this talk at other universities is actually somewhat fun because now's the time when I get to look out into the audience and see people kind of shift in their chairs nervously, not sure what I'm going to say next. I think we can say no, or not necessarily at least. And there's two specific reasons why. All right, the first is that these results are dependent on the actual formulation of SPH that you use. There's recent work which has really made a concerted effort to try to remove some of these strongest deficiencies in the Gadget hydrosolver. And it's also application dependent. There are certain applications where one can find that the hydrodynamic phenomena that are not handled well in Gadget are simply not present. To provide a concrete example of that, this is work that I did with Chris Hayward looking at mergers between Gadget and Arepo. So here the setup is a lot simpler. It's fundamentally different. We took two isolated galaxies and we set them on merging trajectories. They're going to come together, go by first pericenter passage, form tidal features, and eventually come together for final coalescence. Now we can look at, for example, the star formation rates during this merger sequence. And this is what we find. This is showing the star formation rate as a function of time. And there's actually two lines shown here. There's a Gadget line shown in solid, and there's an Arepo line shown as a dashed line. They're nearly on top of one another. So in this situation, we get a nearly identical result. The evolution of this system is almost completely indifferent to which hydrosolver you're actually using. So what actually gives here? After I just talked about how deficient the Gadget hydrosolver can be in these cosmological simulations, why can we get such great agreement here? The answer is that those hydrodynamic phenomena that we expect to be hurting the Gadget results in a cosmological context are simply not present here. Because we've used isolated galaxies that don't have any diffuse gas around them, there's basically no phase boundaries. We don't have fluid instabilities. There's little or no turbulence in these systems. There's no weak shocks, and strong shocks are handled relatively well by Gadget. And there's no need for mixing. So you end up with an evolution that is indifferent to the differences in the hydrosolver. And so in some cases, you can actually get agreement between these two codes still. But that's a bit of a diversion there. What we actually care about is how Arepo compares to observations. So I've now tried to convincingly argue that in fact the results obtained from Gadget simulations are not a good reflection of what should be happening in reality. The question we now have is, do our new simulations agree better with things like the Hubble Ultra Deep Field? Unfortunately, the answer to that is no. So this is showing now the Hubble Ultra Deep Field here that I showed at the beginning in the motivation slide, and I compared against a mock Hubble Ultra Deep Field using these comparison project simulations. The result is that actually the number density of galaxies over here is far higher than the number density of galaxies over here. And the reason for that is that we haven't applied strong feedback yet. In these simulations, we kept them very simple, and without strong feedback, stars form efficiently in almost all halos. So the number density of galaxies over here is far too high than what we expect observationally. Another way to express this problem is by looking at the cosmic star formation rate density. This is showing the star formation rate as a function of cosmic history. The blue line shows the result from our no feedback simulation, and the black dots show observational constraints. What you see is that we're actually almost an order of magnitude off at redshift 0, and we overshoot at all redshifts fairly substantially. So you can easily conclude from this that star formation is far too efficient. So okay, that's not that big of a problem. We already knew that when we ran these comparison project simulations that the feedback we were using was too weak. So that means that if you look at the stellar mass function or the Tully-Fisher relation or the star formation rate density, you do find that our simulations are not providing good matches to reality. However, up until this point, we have been focusing on a numerical comparison. If we want to push towards producing more realistic galaxy populations, we need to include feedback. And we've specifically done that by including galactic winds and AGN feedback, feedback from supermassive black holes. So the second topic I wanted to cover today is a testing of the feedback physics that we've now included into the Arepo simulation. Now that we have validated, at least in our own minds, the hydro solver that's used in Arepo, we now want to know what happens if we include a complete feedback module. How does that help us form realistic galaxy populations?